Hi everyone. In this video, we're going to continue our discussion of chemistry by talking about the different types of chemical bonds. So we're going to address the two primary types of chemical bonds, which are ionic bonds and covalent bonds. And they're differentiated primarily by the way in which the bond actually will exist. So ionic bonds will gain or lose electrons, and covalent bonds are going to share electrons. So we're going to first talk all about ionic bonds, and then we'll compare and contrast to covalent bonds in a couple of minutes. So we drew in the previous video an atom of sodium, and we're going to use that atom of sodium again in order to discuss ionic bond formation. So we know that sodium is number 11, which means it has 11 protons and 11 electrons. So we'll draw the sodium in the middle, and then we'll draw our electrons around the sodium nucleus in their respective shells. So the first shell contains 2 electrons, the second shell contains 8, and then the outermost shell, the valence shell, contains 1 lonely electron. So let's consider for a minute what would happen if we could just get rid of that 1 extra electron. So let's say that electron is kind of like ejected from this particular atom of sodium, and it just is going to float off into space for the purpose of our discussion, and we could redraw the sodium with only 10 electrons. So we'll have the valence shell will contain 8 electrons, and the valence shell will be full because we're now down 1 electron that we had before from the original atom of sodium. So this particular atom is now going to have a positive charge, and we're actually going to rename it an ion. So let's talk about what happened here. In the first picture, we have 11 protons, which means we have 11 positive charges. So we'll draw 1 plus for every positive charge. And we have 11 electrons, so we have 11 negative charges. And since we mentioned that the positive charge is equal in magnitude to the negative charge, 1 positive charge cancels out 1 negative charge exactly. So as long as we have the exact same number of protons as we do electrons, the atom will be electrically neutral, no charge. But in our new drawing, where we ejected 1 electron, we'll draw the positive charges. We still have 11 protons. They didn't go anywhere, so we still have 11 positive charges, but we only have 10 negative charges because we're short an electron. So what that means is if we were to cancel out each set of positive and negative charges, we would have 1 extra positive charge in comparison to the number of electrons that we have. So now we're going to refer to our positively charged sodium as an ion. This particular sodium ion has a full valence shell, so it's considered stable. It's much happier than it was with the lonely electron. And because it's positively charged, any positive ion is considered a cation. If it was a negative ion, we would call it an anion. So this is 1 cation, or an ion of sodium. So before we can talk about ionic bond formation, we need to have another atom that we can use to interact with this particular sodium. So one common example would be sodium chloride. Sodium chloride is table salt. It actually is a prime example of an ionic bond. So let's draw 1 atom of chlorine. So you notice that it's chlorine when it's an atom, and then we'll eventually be calling it chloride, and I'll explain that in just a moment. So we know that chlorine is atomic number 17, which means it contains 17 protons and 17 electrons. So we'll fill in our electrons around the chlorine nucleus. So the first shell contains 2, the second shell contains 8, and the third shell contains 7. Now I mentioned earlier that atoms that exist in the third period can fill up to 18 spaces for electrons in the valence shell, but in this particular case, this valence shell would be considered full if there were 8 electrons. So I really don't want to get into the details of why that would be, but in this case, we're going to consider it to be completely full if we had 8 electrons in the valence shell. So we have 1 empty space, we're short 1 electron, and if we could just put 1 electron in that space, we would be able to consider this shell full. So we ejected 1 electron originally from that sodium atom. It doesn't have to come from that sodium atom. Any electron that's available that's floating in space could fill in this space right here. So that electron will just hop into the space, and now we have a full valence shell. So originally we had 17 protons and we had 17 electrons. The chlorine atom was electrically neutral. But now that we've added 1 electron to fill in the space, we now have a total of 18 electrons. So we have 17 protons and 18 electrons, which means there's one extra negative charge. That negative charge is going to make this a negative ion, which is going to be an anion. It also means that we're going to change the name from chlorine to chloride. So chlorine refers to an atom with 17 protons and 17 electrons. And chloride refers to an ion that has 17 protons and 18 electrons. So now we have a positively charged sodium ion and a negatively charged chloride ion as well. And it's one positive charge, one negative charge. The positive charge and the negative charge are of equal magnitude, and they're attracted to each other. So the positive charge associated with the sodium is going to be drawn to the negative charge associated with the chloride, and together they'll just sort of stick together like magnets. They will form an ionic bond. Let's just review really quickly the tenets that make an ionic bond. One is that an atom has to donate or receive an electron. It could be more than one. Sometimes it'll be like 2 or 3, but it has to donate or receive at least one electron in order to become an ion. So it has to possess a charge. And we know that since opposite charges attract, we can form ionic bonds. Okay, so now let's talk about covalent bonds. So we mentioned that ionic bonds are really about donating or receiving electrons and then having opposite charges attract. Covalent bonds are all about sharing electrons. So let's draw, for example, an atom of hydrogen. So we know that hydrogen is atomic number 1, and it contains 1 proton and 1 electron. So a full valence shell for hydrogen would be 2 electrons, but we only have 1 electron. So if we could fill in that other space for the electron, then we could make a very, very happy hydrogen atom. So what we can do is we can take 2 hydrogens that each have 1 missing electron, and we could bond them together. So now we can draw a molecule of hydrogen where we see both atoms sharing electrons. The first hydrogen is sharing its electron with the second one, and the second one is sharing its electron with the first one. And so together they have 2 electrons between them. So technically, each hydrogen has access to 2 electrons, and it's now considered a very happy and stable molecule. We can draw this a couple of different ways, and I'm just going to demonstrate these because drawing the molecules like this with showing all the electrons is very bulky. So we're going to draw it differently as we sort of move into some of the more complex molecules that we need to draw. So this is equivalent to H2, which I referenced in an earlier video. It's also equivalent to showing the 2 electrons as just 2 dots between the 2 H's, or we could draw a line in between the 2 H's, and that line represents a single covalent bond. So a single covalent bond means that we're sharing 1 pair of electrons. So each atom contributes 1 electron to the shared pair, and the 2 atoms are stuck together by just 2 electrons. So that would be a single covalent bond. Now we can also make compounds with covalent bonds, and a really good example would be water. So water is made of 1 atom of oxygen and 2 atoms of hydrogen. So if we draw oxygen is atomic number 8, which means that it contains a total of 8 protons and 8 electrons. So we'll draw the O in the middle to represent the nucleus, and then we'll draw 8 electrons around the outside. 2 electrons will fill the first shell, and then 6 electrons will fill the valence shell. We know that the valence shell wants to contain 8 electrons, so we have 2 empty spaces where we could share electrons with other atoms. We also just drew the hydrogens before with 1 electron and 1 empty space. So if we were to bind these together, we could make a molecule of water. So we actually will see 2 hydrogens share their each respective electrons with 1 of the empty spaces and sort of share 1 of the oxygen electrons, so that now we can see oxygen has access to 8 electrons in its valence shell, and both hydrogens have access to 2 electrons in their respective valence shells. We write this as H2O, or we can draw sort of similar to how we drew the H's with the 2 dots between them. We can show 2 dots in between the H and the O, and then 2 dots between the other H and the O, and those 2 dots are going to represent covalent bonds, single covalent bonds, and we can just draw those in as lines as well. You can also see that we have two more sets of dots around the O. Those represent the other electrons that aren't participating in the bond but are still present, and those are considered lone pair. It's not super important that you remember that, but I'm just going to try and draw these structures accurately for the time being. So the Lewis dot model is sort of just a way of keeping track of all of the electrons so that we can make sure that we're making bonds that actually make sense and are what the atoms are capable of doing. It's also not super important that you remember that, but we're just going to, again, do it to sort of be accurate. Okay, let's draw one more covalent bond, and I want to do this one because I want to emphasize the double covalent bond. So this time I'm drawing in a carbon, and carbon is atomic number 6, which means that there will be 6 protons and 6 electrons. So 2 electrons in the first shell and then 4 electrons in the valence shell. If there are 4 electrons that are present, that means that there are also 4 spaces where we could share electrons with that carbon. So that carbon is looking to share 4 electrons with other atoms. So carbon is capable of making 4 bonds. So for example, we could take 4 hydrogens and then sort of stick 4 hydrogens around that carbon. Or we could take something like oxygen. We could take 2 oxygen molecules, which we've already drawn, and we'll just redraw a second time, and we could make carbon dioxide. So carbon dioxide is the other gas that we exhale, and we're capable of making 2 bonds with each oxygen molecule and the carbon. So we see now that the oxygen is sharing a total of 4 electrons with the carbon, and then the other oxygen is also sharing a total of 4 electrons with the carbon. So what this means is that we're making a double covalent bond. So if we have a double covalent bond, we have 2 shared pairs of electrons that make up the bond, as opposed to just the one that we showed in the previous examples. Now, there's one other point that's really important about covalent bonding, and that is that we can have either polar covalent bonds or nonpolar covalent bonds. And in order to explain the difference between a polar covalent bond and a nonpolar covalent bond, we have to address this principle of electronegativity. So electronegativity refers to how tightly an atom is going to hold onto its electrons. So something like oxygen is extremely electronegative. It really wants to hold on to all of the electrons that it has access to very, very, very tightly, and it doesn't like to share them all that much. But something like hydrogen is significantly less electronegative, and it doesn't mind letting the oxygen have more access to those electrons than it needs to have for itself. So what that means is that we have this, we call it a dipole. We essentially have this pulling of the electrons towards the oxygen atom that we can see here in the water molecule that we've drawn. And so what we're going to have then as a result of that is this idea of atoms developing slight charges, slightly positive or slightly negative charges, which we also refer to as a partial charge. We use the symbol delta with a plus or a minus in order to represent the partial positive or the partial negative charge. So oxygen, being more electronegative, is going to have better access and hold on to its electrons more tightly. So more electrons is more negative charge, so we're going to give that oxygen a partial negative charge. And then because that oxygen is holding on to those electrons so tightly, the hydrogen by default is going to have less access to its electrons, so it's going to develop a partial positive charge. So we'll draw in the partial negative and partial positive symbols so we can remember that this particular molecule is polar. We can contrast that with the molecule that we drew of carbon dioxide, which is an example of a nonpolar covalent bond. So nonpolar covalent bonds have equal sharing of electrons, and they will have either no charge, they'll remain completely electrically neutral, or they'll have no net charge. So in the case of carbon dioxide, the oxygens are a little bit more electronegative than the carbon, so they might pull a little bit, but this molecule happens to be linear, so the charges are being pulled in opposite directions, and they essentially just cancel out. So we can consider this an example of a nonpolar covalent bond. And we will not draw any partial positive or partial negative charges around it because it's not going to have an unequal sharing of its electrons. Last, let's talk about hydrogen bonds. Hydrogen bonds are not chemical bonds the way that ionic bonds or covalent bonds are. Hydrogen bonds are actually just weak attractive forces between atoms and molecules, so not really considered a bond. We can have hydrogen bonds that form between the same molecule, or they can form between different molecules. So for example, you could have hydrogen bonding between molecules of water, or you could have hydrogen bonding between a water molecule and a molecule of something else. The only elements that are able to participate in hydrogen bonding are oxygen, nitrogen, fluorine, and hydrogen. So you will only find hydrogen bonds between those particular elements. And really, it's one hydrogen being associated with an O, an N, or an F. So we're going to use water as the example. We'll draw some hydrogen bonds between water. So we mentioned before that water is a polar covalent bond. So it's really going to be the polar covalent bonds that are going to participate in hydrogen bonding because we have a partial positive and a partial negative charge associated with parts of the molecule. So we'll just draw them in different colors to keep track, but we'll draw in our partial negatives for all of the oxygens, and then we'll draw in our partial positives for all of the hydrogens. And in the similar way that we would have a positive charge attracting a negative charge when we have the whole charge, if we have a partial positive charge and a partial negative charge, they will also attract each other. The attractive force of a partial positive and a partial negative is not as strong as a full positive and a full negative, but it is strong enough for those molecules to want to associate on purpose. So these bonds can't create molecules. They're not strong enough to actually create molecules, but they can change the shape of certain molecules. So right now we'll talk as a primary example about surface tension. So surface tension is what's responsible for example, if you wax your car and then you have it rains right after that and you see all of the water like beating up on the car, that is a result of hydrogen bonding between the water molecules. Another example would be if you belly flop into a pool. The reason that it hurts so much when you fall into the pool is because you're essentially breaking the surface tension. If you were to dive and only your hands were to hit first, you're using your hands to sort of separate the water molecules and break the surface tension first, so you really aren't feeling the same amount of pain as if you were to belly flop. And then other examples that we're going to find in the human body are things like the way that proteins fold up. Sometimes hydrogen bonds can contribute to protein folding, or even things like our DNA. The way that our DNA is constructed involves the use of hydrogen bonds. Okay, so I think it's important to focus on the big picture, which is that we really want to show that we have these atoms of these different elements, and given the right circumstances, they can stick together. And so far, we've made some very, very small molecules. We've made examples such as oxygen, water, and carbon dioxide. Those are really tiny molecules. But in order to build the human body, we're going to use these exact same elements and atoms. We're going to use the oxygens and the hydrogens and the nitrogens and the phosphorus and the carbon, especially the carbon. We're going to use these exact same atoms and elements in order to build big structures in the human body. So I hope you enjoyed this discussion, and thanks for watching.